Bonjour à tous, bienvenue à ce séminaire de la SFBT, co-organisé par le labo de maths du Havre, LMAH. Et donc nous avons le plaisir aujourd'hui d'accueillir Toni Guillamon de Barcelone, l'Université polytechnique de Catalogne, et donc il va nous parler de maths et neurosciences. Et donc je lui laisse tout de suite la parole.
Merci beaucoup. Merci aussi pour la CFBT pour héberger cet exposé, aussi l'LMH, Aziz, Benjamin et tout le monde là-bas pour m'inviter à faire cet exposé. C'est un plaisir. Et comme je dis, si vous voulez faire des questions, poser des questions pendant mon exposé, je serai heureux de répondre. Je vais changer à l'anglais pour faire l'exposé. Donc, je commence maintenant et je change de langue. Okay. Well, so I'm going to talk about extended response functions. So I have to talk to explain first what does it mean, okay, for oscillatory and damped systems. This is a joint work with some collaborators. Okay, the first of them was Gemma Huguet, who is still now at the UPC. Uriel Castejon, who is now working in a company in data management. Roman Moreno and Kevin Martinez, who are currently PhD students. Okay, so the outline of the talk is well, it has these 4 points. I would say 3 because the last one is conclusions. So I will devote my talk mostly to the first and the third one. The first one to introduce concepts, which are some of them are classical concepts of phase response curves, how to control phase in oscillators. Okay. The field of application is mostly neuroscience, but this can be applied to any oscillator. I will explain also the first results we got and some other people on extending this concept of phase to what is called the phased amplitude response functions. Okay, this involves a series of other concepts like asymptotic phase, isochrones, etc., that I will try to cover in this first part of the talk. The second part I will just cover very quickly to show you, I will show you in the first part what is the what is the new contribution that we make this, okay, what is the extension of the phase response functions that we do. And I would have to give you at least some example to convince you that this is worth for something, okay? So this second point is just show very quickly. I will skip many slides. So it's just to show very quickly what is the, what are the differences or what are the contributions of these extending PRCs, okay? So in the last part is the newest part that we have is the definition of isochrones and phase amplitude functions for foci, for focus, okay? Which it's a little weird because in dynamical systems, we start always studying critical points, okay? And once we know critical points, then we jump to limit cycles, which is the next attractor that is interesting, or invariant manifold that is interesting for us. This is the other way around because classically the PRCs, because of this concept of phase, has been applied to limit cycles, but it makes also some sense to do that in damped oscillations, okay? And I will finish with and I think that is a nice application of that, of how to control sustained oscillations in these damped systems, okay, using minimal energy ideas here, okay? So this is more or less the outline, so you can start sleeping now because I have already spoiled the end of the talk, okay? So let us go to the main concepts that are involved here. So I will try to do, explain the things from scratch for the people who hear about the phase variation in the first time now, and I try to at least give a self-contained talk, okay? So what is a phase variation, or what we call phase variation in this context? Let's assume that we have this can be, for instance, a model of a spiking neuron, okay? Very regular. This is an academic model, of course. There is no noise here. It's a completely regular behavior. And you see here there is a red trajectory that you barely see because you see kind of magenta color, but you see here the red one, for instance, which is the purely periodic trajectory. And now we kick at some moments, okay? So this period is, let's say, t, and we parameterize the period, every period by theta, and theta is normalized from 0 to 1 in this case, for instance. And we kick at different theta times, at different times of the oscillation, okay? And then we see how the peak, where the peak arrives. So in this first one, we don't see too much difference. In the second one, we appreciate that kicking just when it is raising the voltage, okay, this produces a delay of the spike, okay? So the blue spike comes later than the red one. Whereas for the theta equal to 0.6, you see here, we kick just before the threshold of a spiking, and this elicits a spike, a very sudden spike, and this advances the phase, okay? So that's to summarize that for every theta, we have a different phase advancement. So in neuroscience, in experimental neuroscience, this has been used a lot. So that's a way of characterizing a neuron, and so an oscillator, a neuron that oscillates, that does spiking. It's kind of idea of this neuron if you show these curves here, okay? So these curves are, this is theta, and this is the change in theta, okay? How do we compute the change in theta? So with this formula here, this is the time of the regular periodic orbit, and this is the time of the perturbed orbit, okay? This reflects the delay or the advancement of the phase, okay? We normalize this and we plot these figures. We have many plots here because these depend on the strength of the amplitude, okay? But typically this neuron, you can see here that it's a neuron that it has this negative and another set of phases, an interval of phases in which the phase is advanced, okay? So this would be like the identity. Other cells may have a kind of perfect sinusoidal function here, okay? And these different amplitudes, of course, respond to the strength of the stimulus. An interesting one is, what is the limit of these ones, okay? This is smallest one, okay, should be the limit. And this has a name in the literature. People call this the infinitesimal PRC, okay? So the idea of the infinitesimal PRC is that you have the system, you perturb the system, you kick it with some modulus 1 times epsilon, okay? So we need now to have a very weak pulse, and also we consider it very brief, okay? We multiply by a delta function. So in this case, okay, if we have a solution x of t, so the next position after the stimulus is x of ts, the moment of the stimulus, plus the length, well, the vector that we have applied here. And it is well known that the change in phase in first order in epsilon can be written in this way, okay? So it's the change of phase after, well, the difference of phase is epsilon times the gradient at this point here. But this raises a problem. What is this theta bar? The capital theta is the phase, okay? But the phase, I have not defined the phase. Only on the limit cycle I have defined it. How can I compute a gradient if I don't have the whole function, okay? I only have this on the limit cycle, and the phase is constant along transversal directions of the limit cycle. Well, the classical theory solved this in a very elegant way, okay? There are these all result from Malkins and other people has deduced this in different ways, okay? That say that this gradient of theta, even though it's not computable at the beginning, it's the solution of this adjoint equation, okay? And that's very nice because this adjoint equation is a joint equation evaluated, this differential is evaluated on the limit cycle. So you only have to know the limit cycle and impose some boundary condition, of course, because it's a limit cycle and it's periodic, okay? But with this system, with this boundary condition, you can compute the phase response curve, okay? The infinitesimal phase response curve. When I say curve, I mean related to the limit cycle. Okay, so this is the classical theory, but this theory has some problems, okay? Because I have insisted that we have to be on the limit cycle. What happens, for instance, if we infringe some high frequency stimuli, okay? So, or the limit cycle has low characteristic exponents, or the stimuli are too high. too large. Okay, so these are all disadvantageous solutions, situations in which the dynamics is sent away from the limit cycle. Okay, so well, when I say limit cycle, it's the periodic orbit. Okay, so it's sent away. It does not have time to come back to the asymptotic state before we stimulate this again. Okay, so if we have a high frequency stimuli, the first stimulus will send me away, then I will try to go back to my asymptotic state, but since the frequency is high, just suddenly I have another spike, another input, and I'm sent away again from the limit cycle. Okay, so under all these circumstances, so this classical approximation may not work. Okay, and this is the point that we have addressed in several works. Since the talk will be enregistered and this slide more or less tells the same than the outline, I will skip, okay? And I will start with these tools for more general instances than weak coupling or brief stimuli, okay? So these questions that I have criticized here, I want to know how to solve them, how to be able to attack this, give mathematical tools to study the change in phase when I am not on the limit cycle, okay? So that's the first point of my talk, the first message, okay? We need tools to extend this. And well, these are the concepts that are behind this. So let's assume now that we have a system of ordinary differential equations, we parameterize this by the phase because it has a periodic orbit of period t, and the phase now it's between 0 and 1, okay? And we have this limit cycle here. So I'm going to now define what is called the asymptotic phase. We say that the point Q, you see this point here, is an asymptotic phase with P. P is a point on the limit cycle if the limit of the two flows, the distance between the two flows, goes to 0. Okay, so graphically, if you pay attention to the plot now, you see how I move the two trajectories, and I see they always land on the same type of curves. Okay, these curves will have a name. These curves will be called isochrons. Okay, so the isochrons are the set of points that have the same phase with respect to the limit cycle. Okay, well, isochrons have been studied a lot. Okay, so probably the pioneer coining this name was Art Winfrey, but other people like Wilhelmer, for instance, he related this with the stable manifolds. Just remember in the 70s, very recently, there was the theorem of the stable manifold. So they related, in fact, the isochron is nothing but the stable manifold of P, okay? And then later on, many people have studied under different settings. For instance, the paper of de Mongeau and François, they use language of differential geometry. Sabatini, Freire et al. They used well, relationships with Lie symmetries also. And there is a lot of geometrical issues behind that I will not touch now for questions of time, of course. Okay, but well, let's say that this concept of isochron is crucial now for us, okay? So how do we extend this idea of the phase response curve to a neighborhood of the limit cycle, okay? So to do that, what we did was taking advantage of what is called the parameterization method, was a method introduced by Xavi Cabré, Ernest Funtic, and Rafa de la Llave in 2003, 2005, okay? And the idea is very simple, I think, okay? So let's imagine that you have this system, which is, you can imagine a highly nonlinear system with a limit cycle that you cannot compute. And well, it's really difficult. You can only compute it numerically, okay? And then you make this utopy, saying, okay, I would like to transform my system by a change of coordinates k, such a way that the system was the limit cycle was a perfect circle. And moreover, that the dynamics on the limit cycle was monotonous, uniform, okay? So that's a very boring dynamics. And also the dynamics that the orbits that approach the limit cycle also follow the most simple equation possible, which is this lambda is the characteristic exponent of the orbit, okay? And just if I have sigma equal to 0 is the limit cycle. If I am away from the limit cycle, this decays to the limit cycle in a constant rate. Okay. So in this setting, studying isochrones is very easy, okay, because isochrones send also the flow from one to each other. So isochrones here are just straight lines coming from the origin, okay, in this setting. Well, the problem is that there is a relationship, but I don't know K, of course, okay? So the price of this utopy is to find what is K, okay? And of course, they have to satisfy, to be conjugate the two systems, they have to satisfy this equation, which we will call the invariance equation, okay? This is the equation that says that this flow is conjugated with the flow, the simplest flow that we have here, okay? So our strategy is just computing this K, okay? And from this K, taking out all the juice that it has inside, okay? So the first things that we can say is that, of course, if we take sigma equal to 0, we have this limit cycle. So if we apply K to the curve sigma equal to 0, we have the limit cycle of the nonlinear system, okay? If I take a straight line here and I apply K, I have the an isochron of the other system, okay? And also, if I take concentric circles here, concentric circles have the property that all the points of the concentric circle go to the limit cycle at the same velocity, or they spend the same time to go to the limit cycle. I mean, this is a kind of fallacy because they spend infinite time, okay? But you can imagine that there is a colony of ants moving on time and shrinking, and they all are on an invariant curve, which is a concentric circle all the time, okay? These curves, these concentric curves in this setting here are called the isostables of this system. If I apply K to these concentric curves, I have the isostables of the nonlinear system, okay? So far, so good. I hope
Wait,
so. Okay,
is this
thank you.
history?
Sorry? Yeah, can you repeat, please? Okay, I heard something, but I did not understand well. Okay, so so this is the picture. Okay, we have the isochrones. I have not plotted here the isostables, and now look what happens here. If we know the K, and I do some stimulation here, I send my dynamics to this point here, I will be able to know the phase of this point here. Okay, so I will have a new knowledge of the phase difference, which doesn't have to coincide with the knowledge that I have on the limit cycle, okay? Because along an isochron, the phase may change in a different way, okay? And but still, it's true that we have this infinitesimal approximation. And another question is that, well, now we are moving the phase, but we are also moving this variable sigma when we perturb the system, okay? So can we do a similar thing for the amplitude? Okay, this sigma, I will call it the amplitude. This is, in some sense, this is the distance from the limit cycle, but this is not an Euclidean distance, okay? It's a distance a little bit more related to the dynamics of the vector field, okay? So I will just show now how we computed both the phase difference and the amplitude difference in this setting, okay? So the thing is simple, okay? So we had already this infinitesimal approach, okay? And now it turns out that we can compute the gradient from the K. Remember that K, when we fix theta, K of theta sigma is an isochron. If I do the derivative with respect to sigma, I will have the tangent to this isochron. If I do the orthogonal, I have the gradient. Okay, so this is a way from the parametrization to compute this gradient, and then we normalize, of course. Yeah. Okay, so this is a simple way. The big prize here is to compute K. I will not talk too much now. Probably in the last part, how we compute this.
Tony, sorry, we have a question there.
Yeah, sure.
So,
yeah, I see it in the chat. Does the response function represent the K function? Okay, not exactly. Okay, so the response function is defined in terms of the K. Okay, the K is nothing but the change of coordinates. Okay, the change is the reparametrization or the change of coordinates that sends the original coordinates. Well, in fact, it sends the normal form coordinates theta sigma to the original coordinates. Okay, so this K is a map that goes from a domain, a 2D domain or N domain, because this can be applied to many dimensions, to another 2D domain. Okay, and the sheets, okay, of this map, if you fix theta, this becomes an isochron. If you fix sigma, this becomes what I call an isostable. And the response functions are defined in this way as derivatives, okay, of this vector. K is a vector, okay, and the derivative with respect to sigma gives you the approximation of the phase response curve. Is that clear? I hope I have clarified the question. So another thing that we proved is that we can also prove that this solution that you have seen here, this definition, in fact, of the phase response curve, satisfies also this joint equation, and this is very advantageous for the numerical issues, because when we compute this, we have to compute the K, and this is a tough computation. Okay, so we compute the K up to some order, and then having this joint equation allows us to integrate backwards the phase response curves and have the phase response curve extended in a whole domain, almost all the basin of attraction of the limit cycle. Okay. Well, I said that there is also this other variable now, the amplitude. So it turns out that there is a similar thing that we can do. Okay, so this amplitude function, which is defined in a whole neighborhood, in all the basin of attraction of the limit cycle, can be approximated in first order in epsilon, also for the gradient of the function on its level curves. Okay, so we have the possibility to just for free almost to compute the amplitude response function, and turns out also that, well, you can have a definition, very similar one. The only difference is now we differentiate with respect to the theta instead of the sigma, okay? Because this is like an orthogonal system almost, okay? Well, not orthogonal, but transversal.
So if I may, just one quick question, because but the main idea is that to prove this is nice results. I looked at that a long time ago, but it's like in Malkin's theorem or things like. So you take a perturbation and you derive and you obtain these equations, or roughly speaking, no.
Yeah, in fact, here, I mean, to obtain these equations, this is completely geometrical and statical, okay? Because these equations are just tangent vectors, okay, or well, derivatives of a vector restricted to some points, okay? So this is purely geometrical, this definition, okay, which is related to the perturbation is this equation here, okay? So this function that is defined here is controls the difference in amplitude after a perturbation. If I do this perturbation epsilon v, okay, in first order in epsilon, the change of amplitude is epsilon gradient of sigma times the vector field, well, the vector of the stimulus. Yeah, is that clear, Benjamin?
Yeah, no, but there's some more, but just the idea. Yeah, thank you. Yeah.
Okay.
Thank you.
So yeah, so finally, well, this also satisfies a joint equation, okay, which has, in addition, the tendency to the limit cycle, okay. So at the end of the day, what we have done, okay. So let me go back just to insist also in this question that Benjamin has put me, okay. So we had this Malkin situation, okay, this perturbation. This was all restricted to the limit cycle. And we knew this result that the phase change can be related to the gradient of this function, okay? And the gradient of this function satisfies this joint equation that you integrate over an orbit, which is the limit cycle, okay? That's the classical theory. What we have here at the end of the day, so we have the generalization of that, okay? So we have this response function, which now it's applied to any theta and any sigma, okay? So it means that it applies to the whole basin of attraction of the limit cycle. And it also satisfies the same differential equation. And also, we can define the amplitude response function, okay? So this tells me, knowing this gradient of sigma, I can predict which will be the change in amplitude after a stimulus. How away from the limit cycle is this stimulus sending me?
Yeah,
Okay.
interesting.
So just to summarize this, okay, we have what we can call the classical version, which are the PRCs on a limit cycle. And now we create this kind of extended version, okay, in which we not only have the phase response curve, but we have the phase response are functions because they depend on two variables. And we have, in addition, amplitude response functions, okay? So, well, up to now, what is this? This is just a complication, mathematical complication, nothing but this, okay? So it's making, the classical version is very nice because that's the reduction of the dynamics. And we always seek for the reductions, okay? So in some sense, we are on the other way around. But, well, the thing is that there are situations that I insisted at the beginning in which this can be useful. And this is what we have in this second part. I will skip very quickly, just show you the idea, okay? So the paradigm here is that we stimulate, we have a periodic orbit, and we stimulate, we put a pulse stimulus every TS time, okay? So this generates a frequency of the stimulus, okay? If we look at the classical approach, we have always only the phase, and the phase, since this is a periodic stimulus, this creates a discrete dynamical system, okay? Because every time I apply, I have a new phase, a new phase, a new phase, a new phase. Okay, so the phase can be computed from the old one. I have a phase, I apply the stimulus. I know that the PRC controls the change in phase. So I multiply, this is the infinitesimal phase response curve, okay? And then I add, of course, the time that we spend, so the phase that we spend from one stimulus to the next, okay? So this iteration gives us this dynamical system, discrete dynamical system that has been used in the literature to study phase locking, synchrony, and many other related problems, okay? In our case, we can define a 2D approach of that, okay? So this would be the same equation, but now the PRC has been substituted by the PRF because it depends on the two variables, phase and amplitude. And also we have an extra equation which controls the amplitude, okay? I have the previous amplitude plus the change of amplitude by the stimulus. And then, of course, during a time TS, I leave the trajectory flow away to the limit cycle, okay? So this is why we have to multiply by this exponential. And this map can be studied also, and well, we have done several things, and I will show you, but only one thing, in a very simple example in which we know exactly the PRF and the IRF, and we can also compute exactly the change in phase and amplitude. We did a study of how the rotation number, just paying attention to the phase, how the rotation number changes in the two scenarios, the 1D approach and the 2D approaches. And we forced the system to have a high amplitude stimulus, high frequency stimulus, sorry, and also a large amplitude stimulus, okay? So you see these plots here, this axis here is the frequency of the stimulus. If I go to the right, it means the stimulus is very fast. So the TS is very small, okay? And here is epsilon, so this is the strength of the stimulus, okay? So this is just a sweeping, this color map reflects the rotation number. And as you can see in the 1D map, if we use the 1D map to make predictions in this system, okay, we can have errors in this scenario up to the 10 to the minus 2. This means this is a rotation number, okay? So it's the change, the error in rotation number is the error in the angular precision when you do the computation and you want to estimate the next phase, okay? So imagine that you receive about 100 stimulus in a short period. So this error becomes one, of the order of one, which means that that's a huge, the highest error that you can have, okay? So in these scenarios, when you have these big errors here, then the 2D approach is very useful. for high frequency stimulus and a strength, because here we have errors of the order 10 to the minus 4. Okay, so it is 2 orders of magnitude, and this saves this compromise that is presented here. Okay, so this is just to illustrate in which scenarios the 2D approach is valid. Okay, because this is not saying, my message is not saying that the 1D approach is not useful. It's very useful. It has proven to be useful along many years. Okay, so this is just a refinement what we are doing here.
Maybe it's just a question to, because there's a lot of things, and I'm very interested in the talk, but just to I don't want to be lost. Just the general setting is that you have one two-dimensional system and you move it with some kick, or that's right. This is your general setting.
And no, the general setting, in fact, is that we have a nonlinear system, which is it can be n-dimensional, which is this one here. Okay. Yes. And we want to study how the phase changes in this system. Okay. And now I have presented 2 ways to do reductions of that. Okay, one way is to just pay attention to the phase. Okay. If you pay attention to the phase, you have this Malkin setting. Okay, and if you apply a periodic stimulus, this gives this 1D discrete dynamical system that I was saying. Okay.
Yeah, that's my question. You have so your nonlinear system have a periodic orbit, and then the thing is you apply some periodic stimulus, or
in this case, yes. This was just to illustrate the differences between the 1D approach and the 2D approach. Okay.
Okay. So, yeah. It's interesting. Yeah. So just to discuss, so in the first choice, you just consider the phase. And in second phase, you consider the phase and the radius of
the amplitude. Okay, yeah. To cover.
You can think that the standard approach. Can I interrupt?
Yes, of course, Horacio.
You can think that the standard approach. I mean, if you make an infinitesimal kick, then you will most likely not change the amplitude, right? I mean, you will change infinitesimally the amplitude, and then you can assume that there's no change in the amplitude. Now, if you want to use it for realistic situations, when you make a kick to any system, you will also change the amplitude. And if the kick is periodic, then it will never return to the original amplitude of the limit cycle, because it doesn't have time to return before it gets the new kick. And then you will have a new limit cycle in a higher dimensional setup that has a different amplitude. The standard theory assumed that this amplitude was correlated with the phase, so there was no need to study the amplitude separately from the phase. Because in some way that I don't fully understand, then by knowing the phase, you also know. I mean, the knowledge of the amplitude is irrelevant for the knowledge of the dynamics, provided you know the phase. But what Toni is saying is that the amplitude can be uncorrelated with the phase, and it provides that information in another dimension that is not encoded by the phase, and that's why you have to study it, because of just, polar coordinates. It's like polar coordinates as opposed to Cartesian coordinates. You cannot get rid of one of the coordinates and still get all the information. So
yes, thank you, Horacio, because it's a very good explanation. Thank you. Yeah, I was plotting now here. Okay, if I have very short kicks, I leave the dynamics to go back to the limit cycle, so I can use the classical version. Okay, but what happens? That's the other situation. If I do a large kick, okay, and then I go back to the limit cycle, and then before I arrive to the limit cycle, I receive a bursting, for instance, okay? And this is sending even more away to the limit cycle, okay? So all the information that I have in the classical version that is related only to the limit cycle is not worth here, okay? So it's not accurate enough, okay? Because of this uncorrelation that Horacio says, okay? So then if I stop stimulating, this will return to the limit cycle, okay? But these situations here are the situations that I'm worried about, okay? And this is illustrated in this example that I put here. My God, this I have to erase this now. Okay, I didn't know that I would have this problem here. Okay,
Yeah,
so I have to clear that. No.
Okay.
Undo. Okay. Okay, I take this out. Okay, so in this other results that I was showing here, okay, the rotation numbers, okay, I was forcing the situation to be in the second this disadvantage situation for the phase reduction, the classical version. Okay, so when you are here, you can apply the classical theory. But if you have large stimulus or high frequency stimulus, okay, then the classical theory, this shows that the classical theory gives excessive error in, for instance, in the rotation numbers. But this is only an example, okay? So do this periodic stimulus. You could do a noisy stimulus or whatever here at this point. Yeah.
That's nice. I let you follow your, and just a remark. What is interesting, this has been studied again, but like in some PDEs, or you have this phenomena, and the PDE in a reaction diffusion, you will keep your periodic dynamics, but it has been changed in some way, both in amplitude, and you have also this well, this kind of phase locking, and but I don't know how. I know there's some works, but
yeah.
Okay.
Yeah, there are some works about applying PRCs on PDEs. Now I remember some work of Zach Kilpatrick, but there are for sure other people that have worked on that. I guess that Boris Gutkin and Guillamon also. But yeah, I don't know the question in PDEs.
I think your kind of work, it will be very interesting to connect that to.
Yeah, as far as I know. Yeah, as far as I know, this has not been. I mean, the theory as it is here has not been applied to PDEs.
Okay.
Yeah.
Okay, please go ahead. Go ahead.
Yeah, I go ahead now. I will jump some slides here. Okay, this is just comparing dynamics. Since there is a video, okay, so if somebody is interested on that, okay, you go to the video and the paper that is related here, because I think this goes beyond the topic. These are Arnold tongues that I wanted to explain, okay? So, I will now go to the last part of the talk. So I think I have probably 10 minutes or so, Benjamin.
Yeah, we're good. Yeah, we started at like 5, and yeah, 10 minutes is good. Yeah.
Sure. Okay. So let me explain what we have done in the case of a strong foci. Okay. So just extending this. First thing now for focus. Okay. When I have explained what is the phase, I was relying a lot on a point on a limit cycle. Okay. So every point in a neighborhood of the limit cycle in the domain of attraction has the asymptotic phase in generic conditions with the point of the limit cycle. If I try to do that for psi, since I have a singularity, this doesn't work because I have to compare everything with a fixed point, okay? So the concept of phase is not exactly the same, but the concept of isochron holds here, okay? So we can define isochrons as well in the more time way. Let's say, what is an isochron? It's a sheet or a curve, a manifold, okay, that has this property that if I start at one point on the manifold, after some time t, which is fixed, it's the same time for every initial condition, okay? After this time t, I will land again on this manifold, okay? And these manifolds will be the isochrons of the focus, okay? So this is well defined. There are some theorems that say that in generic ways, you always have a continuous foliation of and unique foliation of isochrons in a very generic case of focus, okay? And also the other thing I have used here are the theorems of linearization coming already from Poincaré that say that if you have a strong focus, that is eigenvalues. I'm now in the plane, but this can be also extended to higher dimensions. If I am now have a focus with the real part of the eigenvalue different from 0, then there exists a local diffeomorphism that brings your non-linear system to this linear trivial focus, okay, system. Well, this has some extensions in polar coordinates also. This is equivalent of saying that the polar coordinate of the differential equation depends only on the angular variable. Okay, and also there are some relationships with Lie symmetries and other geometrical concepts. Okay, so these are the tools that we are going to use here. We are not going to use the parametrization method, but this is quite similar. Okay, and the theory that we have, I would not say that we have created the theory, because it's the same theory than for limit cycles. This is adapted and see that everything works. Okay, so now instead of having K, we have this L. L is the linearization. It goes from the nonlinear system to the linear system, the other way around than the K that we had before. Okay, but this is the choice that we made here. Okay, but the theta dot and the sigma dot, they have similar equations, and they can be computed also from the gradients of this transformation, okay, of this change of coordinates. And also if you have a perturbation, then now for the purposes of control, I will call it U, okay, then we can also study at the first order how it changes, how this perturbation changes the phase and the amplitude as well. Okay, so these equations, you have to look at them as a very similar equations to the Malkin equation and the extension that we did for the other equations. We have not put here the epsilon explicitly, but it's implicitly considered here. Okay. So as well, we can define the same way the PRF and the ARF in the same way that we had before. Okay, so now we can have a fixed a singular point, which is a focus, and you can imagine around the focus. Now I will show some picture. You can imagine a foliation of isochrones and also a foliation of isostables. Okay, and on each point we can define how the phase changes and how the amplitude changes as well. Okay. Also, we have these adjoint equations. They are valid also for this setting here. I don't go into the details here, just remind that these are the same ones, okay? And just a question of numerics, okay? So how do we deal this numerically? So we have to compute, this is a key part of the, but I have not insisted too much on the numerics, okay? So we have to linearize we know that exists this local diffeomorphism, but this diffeomorphism may be a series, okay? So we have to stop at some point and we consider this L hat, okay? So what we do is take the invariance equation that I showed before and control the norm of these invariant equations, okay? So we establish a tolerance, okay? And we ask that this error is less than this tolerance for all theta. This leads to have these are also only satisfied according to the tolerance. There is a threshold of sigmas that satisfy this, okay? So normally we work with a high tolerance, let's say 10 to the minus 12, 13 or whatever. And we have a very small domain in which this error is less than this tolerance, okay? We call this domain a fundamental domain. But then, we have this fundamental domain here. Thanks to the these adjoint equations, okay, in this fundamental domain, we can apply the direct formulas to compute the PRF and the RRF, all the response functions. And then using these adjoint equations, we can integrate back and extend the knowledge of the phase and amplitude response functions to the whole neighborhood, okay, to this extended domain, okay. Well, there are a lot of details here. This is just to give an idea of what we call the globalization method. So let's go to the examples. So how much time I have? Probably 5 minutes. And I would like to explain the last part. So this is a first example I took from a paper by Horacio and Andrea Bell. Okay. I will just, this is a self-induced oscillatory system, but I will use it only in the regime of damped oscillations, okay? Well, here I don't want to go into details now. This is only to show how these fundamental domains, how big are they according to the linearization degrees of the normal form that we have obtained. Okay, so I skip this and I show now some results here. For instance, you can see in blue the isochrones. Okay, and these dashed lines are the isostables. There are 4 isostables here. This big one, the yellow one, this red one that you almost cannot see, and another blue one here. And on the right, you have the phase response functions associated on every one of these isostables. And you can see here how it changes abruptly, okay? The blue one is the closest to the origin. And there, the systems behaves as a completely linear system, okay? But if you go away, so this sinusoidal function is distorted, okay? And you can have very interesting response functions that go from negative to positive parts, okay? So you can, this is very useful to know how, where I have to stimulate to get an advancement or a delay, okay? Well, I have another example here. Yeah.
Yes, we can leave the discussion then for later, but.
Yeah, yes, okay.
Okay,
So,
I'll let you finish and then we can have this.
Okay, thank you. So yeah, otherwise now I get a little bit nervous because of time. I don't want to be so long. So let me explain at least the idea of this part that we have been working also. Okay, the idea now is I have a system with a damped oscillation, okay, and I want to exert some control on the system in such a way that I can have a sustained oscillation. Okay, so I want to create a limit cycle from a damped system. Okay, and I want to do that minimizing energy. Okay, I want to do that in an optimal way. Okay, so following the ideas of Monga, Merlis, and this group that they have used a lot this for limit cycles as well, and also for some critical points. Okay, we just pose the question as a variational problem. Okay, in which we have the phase and response functions that drive the system. Okay, and these are used as constraints because they predict the changes in phase and amplitude. Okay, and we put that these constraints. These constraints are for the periodic orbit to close. Okay, and then we have this cost function here, which mostly says that we want to minimize this energy. U of t is the, is the stimulus that we put to the system, is an time-dependent stimulus, okay? So we would like this to be 0, but if this is 0, we don't have limit cycle, okay? So we want the minimum energy here. We penalize the fact that we go far away from the initial condition as well. And also there are 2 other conditions here, which are the Lagrange conditions for the 2 differential equations of the phase response and the amplitude response function. Okay, so we have this variational problem. Want to minimize this, we use the Euler-Lagrange setting, and we finally are led to a system of differential equations in these variables, in the Lagrangian multipliers, and also the phase and amplitude. And also, after solving this, we have an explicit function, which is the solution of the Euler-Lagrange equation, that gives us what is the U of t, what is the stimulus, what is the control input that I have to put to achieve this optimal limit cycle. Okay, so we think that this can be useful also for just kind of reanimation problems. Okay, or you wanna, if you have a cell that is oscillating in a damped way and you want to create a sustained oscillation, this can have many applications. Well, I don't go now into the technical details, but we solve the problem. We get a U, and this U is plugged into the system. Such a way we have this periodic orbit, which is the solution of the system. Let me show to finish one example, a couple of examples of this. This is a linear focus, okay? This is just to have the idea here. This linear focus has alpha equal to -1, is a attractor, and beta, we have played with 2 betas. And look, this is beta equal to 1, and this is beta equal to 10, okay? Beta means, equal to 10 means that this focus spirals very fast, okay? And it's faster than the attraction to the point, okay? So you see that in this way, it seems easier. You get a very nice orbit that almost doesn't go away from the previous isostable. Okay, whereas if you have the spin velocity small enough, so the orbit, you start here, for instance, and the dynamics of the system sends you to the fixed point, and the control takes some time to recover and to realize that it has to be strong enough to recover this and force the periodic orbit. Okay, and this is can be also seen here. So beta equal to 1 is here. We have to spend more energy when beta is very small, when very big. When we have high velocity, spin velocity, then we have to spend less energy. Also, if we ask, because this TPO is the period that we are asking, imagine that you can solve a problem of jet lag, okay? And you have a period of 24 hours and you want to force the period to be 18, okay? So the quotient between the two of them would be 0.75. You will be here, okay? Here it's already expensive to do that. Of course, if the period that you ask is closer to 1, then you get better, better solutions, less energy solutions, okay? Well, so we have applied also this to this Fitsu-Nagumo case, but I think this is another example. It's late already, and it's moment to go to the conclusions. Just summarize. I think that this first pass has been already summarized, that I have presented these extended phase and amplitude response functions that are useful for high frequency, low characteristic exponents and large amplitude stimuli, okay? And in the last part that we have run a little bit, okay? But we have seen that we can apply this to damped oscillations, and by adding a control mechanism, also we can create sustained oscillations from damped systems in an optimal way, okay? We think this can have potential applications to neuroscience, generation of circadian rhythms, etc. There is a whole literature on noise-induced stability. Okay, another example we have not yet tried, and we want to do that now, is to use this for unstable foci. Okay, so you have an unstable focus, and you want this to transform into a stable limit cycle. Okay, using this energy control. This is very related to this noise-induced paradigm also as well. Okay. Well, I think that's enough. I should stop here and apologize for the extension, not of the phase, but of the time. Okay.
No, the time was perfect. Thank you, because we interrupted you a couple of times, and no, it was perfect.
Well, yeah, I asked that, but yeah, thank you very much, and thank you for interrupting me, and please continue interrupting from now on. Thanks a lot for your attention.
We are going to thank Toni for this very nice talk. I'm just clapping by hand. And so, if you have questions to Toni, please go ahead.
Yes, I do.
Yeah. Sure.
Yes.
I have a question, a couple of questions. Can you go back to the figure that
your model? No, the moment that you were here. Yeah.
Yeah, this one. So, what do these perturbations? What do these different isostables mean in practice?
Yeah. So this every isostable means if you take 2 points on the same isostable and you integrate the system on, okay. After some times, imagine that you have a point here. Sorry, I have a problem with the mouse now. Imagine that I have a point here. I integrate on time, okay, and I land on this yellow one, okay. Mm-hmm. I take another point here. I integrate the same amount of time, the same, okay. I will also land on the same isostable. That's the meaning of the isostables, okay. They control how far away they are from the limits, from the fixed point in this case, okay. Well, this is a way to say far away. In time, they're always infinitely away, okay. But these are the level curves of the distance to the point, in some sense, in the time distance to this point. Yeah.
What do they mean in practice if I perturb the cell? Will I get different? I mean, my question is, because I'm missing the intuition here. Do they in any way mean that if I perturb the cell, I can get different results.
Yes. Well, if
because the limit cycle is not well. I mean, does it create some type of degeneracy?
Well, I don't know if a degeneracy, but it's true that this says if you only pay attention to the phase, okay, what happens? I mean, these points here, they have all the same phase, okay? Well, they should be a vertical line, okay? I'm sorry, I am a little bit clumsy. Okay, so but now I say in the same phase, if I am in this outer isostable, which is the purple one, I will not notice any change in phase, okay? But if I am in this yellow one, in the same phase, I will notice a big change. So in the same phase, I mean the same isochron, okay? So it's not the same to perturb in this point and on this point here, okay? It's sensitive to the distance to the origin, okay? The phase. If you had a perfect linear system, it wouldn't mind, okay? Because it doesn't mind where you are on the basis of
okay, so it captures the nonlinearities.
It captures the nonlinearities.
Captures the nonlinear effects.
Yes, yes, yes. Yeah.
So to some extent, you're saying that if you have a linear system, then you will have only one of these isostables.
Well, no, you would have several of them, but all concentric. They will be very, very boring, okay? The isostables would be that, okay? I mean, concentric circles around the limit cycle, okay?
Okay.
This would be, and the isochrons would be straight lines, just radial straight lines.
So they will all look like the blue lines.
Yeah.
The blue lines.
Yes. Yeah.
The blue lines, but with different amplitudes.
Yes, yes. In fact, one of the examples that I have skipped was that. Okay, well, I think it was here in the linear one. Okay, this one you see here. Okay, they have different amplitudes, of course, because you are at a different distance of the point. Okay, but the shape is exactly the same. This is the linear case, no? And the other one, you see, if you have nonlinear cases, then they are distorted a lot. Okay.
Okay, so if you go back to the figure.
Yes, I go back. I was cleaning up the mess. Okay, so I go to this one again. Yes.
Okay, so then to some extent, the shape of this isostables is a measure of the complexity or of the nonlinearity of the system. Right?
Yes.
So if
yes,
you have a system that is quasi-linear, say this parabolic type of models, then you will have deformations of the sinusoids, and the fact that you have this.
You say. Sorry, I was about to say something else.
The fact that you have this, the yellow one in particular is probably due to the synaptic current. So to some extent, it can serve you to infer the nonlinearities of the model.
Yes, yes, and also, for instance, in some, I was trying to look now for some example in which they were also slow fast systems. Okay, so this notices a lot of the slow fast properties. Here, I don't know exactly. You know the system also, but better than me. But I would say in these changes of curvature, I'm sure that here there is some slow fast issue. I mean, there is a change.
Yeah, and there is.
So this is also captured by the isochrons in this case, and also by the position of the, of course, because I mean, if you are in a slow region, okay, you have to be closer geometrically to the fixed point to spend the same time at another point which is in a fast region. Okay, so these shapes, I mean, the slow, these moves, it changes the concentricity of these curves. Okay. This shifts the curves towards some direction. Okay, so yeah, a wise lecture of these pictures can tell also about the slow fast properties of that. Yeah. Of course, there are other ways to tell about the slow fast properties, of course, no? But yeah, this would be one way.
The other question that I had is when you make the perturbations for the control perturbations.
Yeah.
So first of all, I think you can do that also when there's no a focus but a stable node. But it's a different discussion. Perhaps it's longer and we can have it separately.
Yes,
but when you do the control, then you can connect that with the noisy systems, because noisy systems, essentially what they do is just random. You can think about a noisy system as a sequence of random random finite perturbations of different amplitudes, in which case they are essentially recreating the limit cycle around.
Yeah, you mean Horacio, to put the stochasticity here, subsetting this U of t, this could be also a noisy term.
Yeah, so if you put stochasticity, you will get a limit cycle.
Yeah, but
because you're activating the transients. All you are doing with this control thing is you're activating the transients.
Yes. In fact, that's why I was comparing also with the noise-induced situation. I think that this would be quite equivalent to have this noise-induced scenario that people has studied also. Okay, what you are asking now, I think, and what my version here is a deterministic version of that in some sense. Yeah?
Right, exactly. Yeah, and you can build another deterministic version by considering. I mean, the noise is essentially a continuum of infinitesimal kicks.
Yeah.
What you can do is you can make kicks of finite size, like square pulses of finite size, like step functions of finite sizes, where you keep the size constant.
Yeah.
You make the input finite, but then you keep the amplitude random.
Okay.
So then you have a deterministic system. The system, once you constructed the input, the system becomes deterministic, but you have the same effect. In fact, there is a theorem that guarantees, I don't remember the name, but there's a theorem that guarantees the convergence. And then you have a deterministic system that achieves more or less the same effect as a
noise system,
a stochastic system, and it may serve the purpose of controlling. I've tried it with a couple of things, and I think it works. I can tell you more about it.
Okay, thank you. Yeah, it's a very nice idea. Yeah, thanks. And about the nodes, I'm sure that can be done, the problem of control. The only thing is in the setting I have presented, I rely on the monodromy, okay? So to define my PRFs, and so in this setting, we should change the setting probably, yeah? Deal that in another way. But yeah, philosophically it can be done, in principle. Thank you.
Do we have another question? Does somebody want to ask something to Toni before he leaves?
No.
I can stay here for the whole afternoon.
Okay. So we will thank Toni again for this very nice talk and all the comments around. Thank you again, Toni.
Thank you for your attention and for inviting me also. It's been a pleasure.
So I have a couple of announcements and then I will close the registration. So next month there is again a seminar organized by the SFBT and Le Havre. So the next speaker should be Jacques de Mongeau. It's in February, but we don't know the exact date, but I will keep you, or somebody will keep you posted. I don't know who.
Okay.
And, donc je termine la session d'aujourd'hui. Donc c'était un grand plaisir d'avoir avec nous Toni Guillamon pour ce premier exposé dans le cadre du séminaire de la SFBT co-organisé par le LMAH. Donc le mois prochain, on aura un exposé, il y a un exposé de Jacques de Mongeau qui est prévu et vous serez tenu au courant. Voilà, donc merci encore Toni pour ton super exposé.